Hi! Napier's number is arguably the most important constant in mathematics. In this video, we'll look at how it is defined. To do so, we will follow Bernoulli's argument on compounded interest rates, which is, by the way, an interesting topic for our everyday life. Now, suppose we have a sum S, and we want to deposit this amount in a bank. The bank offers an annual interest rate R, which is assumed to be positive here. This means that at the end of the year, we'll have our initial sum, S, plus a bonus proportional to S. This coefficient is just the interest rate. So the mechanism is, at the end of the period, we have 1 plus the rate times the initial amount. Now, suppose we compute this rate in a slightly different way. We divide the year into two equal periods, two 6-month periods, applying on each period half of the rate R. So initially, we have the amount S. After 6 months, the bank pays the rate R half. So we will have this amount, 1 plus the rate, which is R half now, times the sum, S. After another period of 6 months, the bank pays again the rate R half. So we will have 1 plus the rate times this sum. And this makes S2 equal 1 plus R over 2 square times S. This way of computing interest rates is called compounding interest rates. Now, a natural question arises. Is it better to compute the rate in this way, so once per year, or twice but half of the rate per year? Now, we can easily respond to this question by just comparing these two coefficients in front of S. In fact, if we expand 1 plus half square, we see that since the last term is clearly positive, this expression is larger than 1 plus R. So this coefficient is larger than this one, and this means that S2 is greater than S1. Now let's divide the year into 3 equal periods, applying a rate R over 3 on each period. So initially we have our amount S. After 4 months, the bank pays the first time the rate R over 3, so we have 1 plus the rate times S. After another period of 4 months, the bank will pay again the rate R over 3, so we will have 1 plus R over 3 times the amount we had here. So 1 plus R over 3 square of S. And finally, after other 4 months, we arrive at the end of the year, the bank pay again the rate R over 3, so we end with the sum 1 plus R over 3 cubed times S. Now, it is better to compute the rate 2 times taking half of the rate, or 3 times taking 1/3 of the rate. Again, we can easily respond to this question by directly comparing these two coefficients. We may observe that if we expand the cube here, we get this. Now, the last term is positive, since here we are assuming that R is positive. So if we throw away, we just reduce this sum. And moreover, the square term, R square over 3, is larger than R square over 4. So if we replace this by this, the sum still reduces. And this thing is exactly 1 plus R half square. So this coefficient is larger than this one, and this means that the sum S3 is greater than S2. At this point, we can extend the interest calculation by dividing the year into n equal parts, applying a rate R of n on each period. We have already seen what happens when n is equal to 1, 2, 3, and easily we can guess what happens for n equal 4, for n equal 5, and for a generic n. Now, it is possible to prove that what we have seen to be valid for the first 3 elements of this sequence is valid in general. So that is, if the rate R is positive, this sequence of coefficients is increasing. So from the perspective of the account holder, the best approach would be to divide the year into an infinite number of periods and applying on each period an infinitesimal rate. That is more precisely to take the limit for n going to plus infinity of this quantity. Now, calculating this limit is not at all simple. The base, as you can see here, goes to 1, while the exponent goes to plus infinity. So we are dealing with something like 1 to plus infinity. Now, what happens to this expression? One might think that since 1 to something is equal to 1 always, then also 1 to plus infinity will be equal to 1. In fact, many people think this. But we can see in this example that the answer is certainly not correct. Indeed, this sequence is increasing, so all the elements are bigger than the first one for n equal 1, which is 1 plus r. And 1 plus r is greater than 1 because r is positive. So clearly that limit cannot be 1. In fact, 1 to plus infinity is an indeterminate form. And we can see this with an informal argument as follows. Remind that exponential and log are one the inverse function of the other, so we have this remarkable identity, x equal 2 to power log base 2 of x. We use this identity with this quantity, 1 to plus infinity. So we get this, and then we descend the exponent here in front of the logarithm. So we end to 2 exponent plus infinity times log base 2 of 1. And since log base 2 of 1 is 0, we realize that here there is an indeterminate form, infinity times 0. So it is not a trivial result, then, to prove that the following facts hold. First, there exists a limit when n goes to plus infinity of 1 plus 1 over n to power n. This is the case r equal 1. This limit is finite and defines a number denoted with letter E, which is called the Napier number. This number is between 2 and 3, is something like 2.78, and it is moreover an irrational number. And more in general, when you put a rate here, a number r here, this limit exists and turns out to be equal to that number e to exponent r, whatever is the number r real. Okay, that's all. So what can you do now? The first thing I would suggest to you is to practice the exponential limit by computing limits like these ones. And if you want a more challenging task, you could try to prove to be Bernoulli for one day, for example. Why not? So you could try to prove the following fact, that assuming this inequality to be true, this is called the Bernoulli inequality, then this sequence 1 plus 1 over n to the n is increasing. Now we have checked this for the few first n equal 1, 2, 3, and with this inequality you should try to prove that it is true for every n. So that when you put n plus 1 here, you get something bigger. Good luck.